Let us solve one more problem on the design of stator of induction machines. The question is, estimate the stator core dimensions, number of stator slots and number of stator conductors per slot for a 100 kilowatt 3300 volt 50 Hz 12 pole star connected slip ring induction motor. Assume average gap density is equal to 0.4 Weber per meter square. Conductors per meter is equal to 25,000 ampere per meter. Efficiency equal to 0.9. Power factor is equal to 0.9 and winding factor is equal to 0.96. Choose the main dimensions to give best power factor. Also, the slot loading should not exceed 500 ampere conductors. Okay, so estimate the stator core dimensions. First of all, we have to find out the main dimensions of the stator, that is D and L. Okay, first of all, we have to find out the main dimensions D and L of the stator. So we know that the main dimensions are always calculated from the output equation. So we have derived the output equation for the kVA rating Q. Our output equation is Q is equal to C0 D square L into Ns. But in case of induction machines, the value given in the question is the machine rating, the rating of the induction motor, that is output power in kilowatt is given. 100 kilowatt. Here this 100 kilowatt denotes the output power in kilowatt. But for an induction motor, electrical power is in the input side. So we have to convert this power to the input power, and it should also be converted from kilowatt to kVA, because we have the equation for kVA, electrical power in kVA. So this output power has to be converted to input kVA. This is the first step in solving problems on induction machines. So we can calculate input kVA as output kilowatt rating divided by power factor into cos phi. Power factor into efficiency. Output kilowatt divided by efficiency. Output by efficiency gives the input power in kilowatt. Then input power in kilowatt divided by cos phi gives the input power in kVA. So first of all, calculate the input kVA Q, which is output kilowatt rating, that is 100. Here it is 100 kilowatt. 100 divided by power factor is given as 0.9. and also the efficiency is 0.9. So 100 divided by 0.9 into 0.9. So answer will be 123.5 kVA. Okay. Now substitute this value in all the given values in the output equation. That is Q is equal to C0 D square L into Ns. Here C0 is 11 into B average into AC into kW into 10 raised to minus 3 into D square L into Ns. So we have Q, the input kVA as 123.5. So this is the equation for power in kVA. So the value of Q should be substituted as kVA itself, which is equal to 11 into. So in the question, the flux density is given. Average gap density is given as 0.4 Weber per meter square into AC. So the conductors per meter is given, which is nothing but AC, and it is equal to 25,000 amperes per meter into kW. kW is the winding factor, which is given as 0.96 into 10 raised to minus 3 into D square L into Ns. So Ns is the speed in RPS. We can calculate Ns as 2 into F by P. that is 2 into frequency 50 Hz divided by P. Here in this question, the number of poles is given as 12. So the synchronous speed in RPS, Ns is equal to 8.33 RPS. Okay. Now, we can calculate d square L from here. So d square L will be equal to 123.5 divided by 11 into 0.4 into 25,000 into 0.96 into 10 raised to minus 3 into Ns, that is 8.33. So the answer will be, on solving this fraction, the answer that we are getting for d square L will be 140.4 into 10 raised to minus 3 meter cube. So unit is meter cube because it is d square into L. D and L are in meters. So we got the value of d square L. In the next step, we have to separate the value of d and L from the product d square L. Okay, for induction machines, this separation is based on the value of L by 2 ratio. For different design specifications, different values of L by 2 ratios are there. But here in this particular case, the design specification needed is the best power factor. In the question, it is given that choose main dimensions to give best power factor. So the relation for best power factor is, the relation is the pole pitch tau is equal to square root of 0.18 L. Pole pitch tau is square root of 0.18 L, where L is the length of the stator core. So we know that pole pitch tau is equal to pi d by P. So pi d by P is equal to square root of 0.18 L. So on solving this, we will get pi into, so let us square both the sides. So we will get pi square d square divided by P square. P is the number of poles, that is 12 square, is equal to 0.18 L. So from this, on simplifying this relationship, we will get d square is equal to 2.63 L. D square is equal to 2.63 L. Okay. So we have d square L as 140.4 into 10 raised to minus 3. And we have got the value of d square in terms of L. So substitute the value of d square in this equation, in d square L. So it will become 2.63 L into L. That is 2.63 L square is equal to 140.4 into 10 raised to minus 3 meter cube. Okay. So from this, we will get the value of L. So L will be equal to 0.23 meter. After getting the value of L, substitute the value of L here. So 2.63 times L will be d square, and from that we will get the value of d. So I am not going into the detailed steps because all these are very simple steps. So d will be equal to 0.78 meter. On separating d and L using this relationship, tau is equal to square root of 0.18 L. We will get the value of diameter of the stator as 0.78 meter and length of the stator core as 0.23 meter. So thus we have got the main dimensions of the machine. Okay. Thereafter we have to calculate the number of stator slots, the number of stator conductors per slot, etc. So in order to calculate the stator conductors per slot, first of all we have to calculate the stator turns per phase, TS. So let us move on to the calculation of TS, stator turns per phase. TS. So in induction machines, the turns per phase is denoted as TS. But in case of synchronous machines, it is simply denoted as T phase. But here, as there can be conductors both in stator and rotor, in order to distinguish between them, we have to denote it as TS and TR. So stator turns per phase is denoted as TS in case of induction machines. But it is simply T phase in synchronous machines. So equation for TS is, we have the equation, that is ES, stator voltage per phase divided by 4.44 into F into phi into kW. So this is the equation for calculating TS. ES divided by 4.44 into F into phi into kW. So here ES is the stator voltage per phase. ES is the stator voltage. This is one of the important points that we have to listen to, because there may be some cases where we will simply put the value of voltage as that is given in the question. But we have to check whether the winding is connected in star or in delta. And depending on that, we have to calculate the phase voltage. Okay, ES is the stator voltage per phase. It is the phase voltage. Stator voltage per phase. Okay. So now in this question, it is given that the stator is star connected. 12 pole star connected slip ring induction motor. It is given in the question. So in case of star connected, we have the phase voltage is equal to line voltage divided by root 3. Line voltage divided by root 3. So the value given in the question, that is the 3300 volt, is nothing but the line voltage. So voltage per phase is line voltage divided by root 3. 3300 divided by root 3 volt. Now frequency is a known value, and then next it is phi, the flux per pole. So phi is not given in the question, so we have to calculate the value of phi. So always in design problems, we are calculating the value of phi from the given value of B average. Okay, we know that B average is equal to P phi divided by pi d L. Okay. So B average is known, number of poles P is known, we have calculated D and L. So from here we can calculate phi. Phi is equal to B average into pi d L divided by P. So we will get phi is equal to B average is 0.4 into pi into the value of D, diameter is 0.78 into 0.78 into length is 0.23 divided by number of poles is 12. Okay, on solving this equation, the value of phi will be 18.8 into 10 raised to minus 3 Weber. Okay, so substitute phi and ES in this equation, then we will get the number of turns per phase. TS is equal to ES, that is 3300 divided by root 3 whole divided by 4.44 into F, that is 50 hertz, into phi is 18.8 into 10 raised to minus 3 into 4.44 F into phi into kW, that is 0.96, the winding factor. So the answer that we are going to get is TS is equal to 487. Okay. So this is the number of stator turns per phase. So now we have to calculate the total number of stator conductors. So total number of stator conductors is Z, which is nothing but 6 times TS. So Z is equal to 6 into 487, which is equal to 2922. Okay, So we got the number of stator conductors. Now we have to design the slots, that is number of slots. Okay. So for calculating the number of slots, we know that for large machines, the slot pitch should be in the range 15 to 25 mm. So here we are considering a 100 kilowatt machine, which is a large machine. So the slot pitch should be in this range, 15 to 25 mm. Okay. So the procedure that we are generally following to calculate the number of slots is that we'll choose different values for slots per pole per phase. Q is equal to 2, Q is equal to 3, Q is equal to 4, etc. And we will check whether the slot pitch in these cases comes under the specified range. So first let us consider Q is equal to 2. That is, slots per pole per phase is equal to 2. Implies the total number of stator slots is equal to Q into number of poles into number of phases, which is equal to 36 into 2, that is 72. Now check whether in this particular case the slot pitch is within this range. So we have slot pitch is equal to slot pitch YSS is equal to pi d by SS, circumference of the stator divided by number of stator slots, which is the distance between two adjacent slots, which is equal to pi into 0.78 divided by 72, and the value will be around 34 mm. So value corresponding to Q is equal to 2. Value of slot pitch corresponding to Q is equal to 2 is almost 34 mm. So which is outside this range. So we cannot choose the slots per pole per phase. Q is equal to 2. So now let us go for Q is equal to 3. So for Q is equal to 3, the slot pitch will be, total number of slots becomes Q into number of phases into number of poles, that is 36 into 3, 108. Now calculate the slot pitch. It will be pi d by SS, that is pi into 0.78 divided by 108, and the value of slot pitch will be around 26.68 mm. So which is inside the range 15 to 25 mm. So we can choose the value of Q as 3. It is okay. Okay. So for Q is equal to 3, the corresponding value of total number of stator slots is 108. Now we have been asked to calculate the number of conductors per slot. So for this combination, the conductors per slot will be total number, let us denote it as ZSS, conductors per stator slot. It will be equal to total number of conductors divided by total number of stator slots. So we have already calculated Z as 2922 divided by total number of stator slots 108. So answer will be approximately, so it should be an integer, conductors per slot should be an integer. So it will be approximately 27. Okay. So we have calculated all the required values, but there is one condition given in the question. That is, the slot loading should not exceed 500 ampere conductors. 500 ampere conductors. For this particular value of conductor per slot, we need to calculate the slot loading and check whether it is less than 500. So we can calculate the slot loading as, slot loading means how much a slot is electrically loaded. So it can be calculated as current in one conductor into conductors per slot. Number of conductors per slot into current in one conductor. So we know the conductors per slot, that is 27. Now we need to calculate the current in one conductor. So current in one conductor is nothing but the phase current Is. So current in one conductor is the phase current, because here we are considering only one parallel path per phase. There is only one if we are considering a phase, current flowing through the phase is I phase, and we are assuming that there is only one parallel path in one phase. So all the conductors will be connected in series. So per phase current and current in one conductor are the same. So we need to calculate the per phase current Is. Okay, phase current we need to calculate. So how will you calculate the phase current? And always remember that while calculating the phase current, it should be from the kVA, power in kVA. Okay, electrical power in kVA. So we have the input power in kVA, Q as 123.5 kVA. Okay. So also we know that three-phase power Q is equal to root 3 into VL into IL. So we can calculate IL, the line current IL as Q divided by, that is 123.5. It should be converted to volt ampere, because we are expressing voltage in volt and current in amperes. So Q should be converted to volt ampere. So 123.5 into 10 raised to 3 divided by root 3 into VL, that is root 3 into the line voltage is 3300. Okay. So answer will be 21.6 amperes. So stator current is the line value of stator current IL is 21.6. So here in this question it is given that the stator is star connected. So we have the phase current Is is equal to IL, which is equal to 21.6 ampere. So slot loading is equal to stator current per phase or current in one conductor into number of conductors per slot, that is 27. 21.6 into 27, and it will be 583. Answer will be 583 ampere conductors. So which is beyond the given limit. It is given that the slot loading should not exceed 500 ampere conductors. But for this particular value of slots that we have chosen, the slot loading exceeds 500 ampere conductors. That means we cannot use the value of total number of stator slots as 108. That is, the value Q is equal to 3 cannot be used for slots per pole per phase. So then what is the solution? Go for the next value of Q. That is, choose the value of Q as 4. Okay. So let us choose Q is equal to 4. Then total number of stator slots will be equal to Q into number of poles into number of phases. And that will be 36 into 4, 144. Total number of stator slots is 144. Now calculate conductors per slot. Which is equal to total number of conductors divided by total number of stator slots, which is 2922 divided by 144, and it will be approximately 20. Now for this combination, calculate the slot loading. Slot loading. So we know that slot loading is current in one conductor Iz into number of conductors per slot ZSS. So which will be 21.6 into conductors per slot 20, and it will be 432 ampere conductors. Okay, so we know that we can see that this value is less than 500 ampere conductors, which is inside the given limit. So we can accept this particular design. That means the total number of stator slots that we have to choose is 144. And conductors per slot equal to 20. Okay.